Well, welcome back to our discussion about analysis of graphs and the attributes of functions. And so in this video, we are going to focus our discussion on two key elements. One is we're going to talk about how do you determine if a function is even or odd from either its graph or its equation. And the other thing we're going to talk about is how do you evaluate a piecewise function. So let's jump in. So when we're talking about functions, sometimes we classify them as even or odd functions. What that means is there is a relationship with symmetry in their graphs, and there's also a relationship with how the function relates to either a negative variable or a negation of the entire function. So we're going to focus on even functions first. Okay, so when we're talking about even functions, we can say that if we're looking at the graph of an even function, the graph will be symmetric with respect to the y-axis. What does that mean, symmetric with respect to the y-axis? Well, it's like the y-axis acts as a mirror, and everything on the left side is mirrored to the right side, or vice versa. Everything to the right side will be mirrored over to the left side, but it will look like that y-axis splits the graph precisely in half. Okay, and so this is an example of an even function. Notice that that y-axis, it looks like the y-axis just cuts that parabola right in half, and indeed it does. So there are lots of different types of even functions, and all of them will have that attribute. They're symmetric with respect to the y-axis. Now, how do you determine by looking at the equation whether it's even or odd? Well, the algebraic test is going to look like this. If a function is even, then this will be true. F of x will also be equal to f of negative x. And you can see why that's true here. Okay, if you're looking at this graph, notice that the y value that happens at every x value will be the same as on the other side, right? That's the whole mirroring process. F of 2 is the same as f of negative 2. They're both 0. F of 3 is 5. F of negative 3 is also 5. And f of x is going to be y, while f of negative x will also be y here. Okay, so what we do then is we take a function's equation and we test to see whether or not it's even by subbing in negative x and seeing if we get the same result as we started with. So let's look at this function. F of x is equal to x squared minus 4. What we want to do with this is substitute in negative x for every x. All right, so here we go. F of negative x is equal to negative x squared minus 4. Now I'm going to simplify this. What is negative x squared? Well, that's negative x times negative x, but that negative times the negative gives me positive x squared. So f of negative x is x squared minus 4, which is the same as f of x. And so since they are equal, this is an even function. And of course, that is what we expected because this is the equation of this function that we examined. Okay, so when we're talking about an odd function, we will first think about the graph. We can recognize the graph of an odd function because it will also have some symmetry, but this is rotational symmetry. It will be symmetric with respect to the origin, and that's a little bit different. Okay, and what that means is if you were to take the graph and stick a pin in the graph in the origin and then spin it upside down, rotate it 180 degrees, it should look exactly the same. Okay, so let's look at a graph. This is a very simple odd function, okay? And I want to demonstrate what I'm talking about with spinning this 180 degrees. Look, take a good look at what this function looks like, and it's sitting the way it should on the coordinate plane. Now, if I spin it 180 degrees, keeping that origin right intact, it looks exactly the same as how it started. And that's a visualization of what an odd function looks like. So let's put it back in place. All right, now what's the algebraic test? The algebraic test is similar to the even function. It is f of negative x is equal to negative f of x. So we take the result of what we got when we tested for even, and we compare it to negative f of x. Now, at first glance, you might think that those look exactly the same, but they're really not. In this first one, we are negating the variable and then simplifying the variable. In this second one, we're negating the whole function. So this is the same as putting parentheses around the entire function and putting a negative in front of it and then distributing the negative all the way through. Okay, so let's take a look at this one. All right, so f of x here is x cubed. So first thing we need to find is what is f of negative x. When I sub in negative x for x, then I'm taking negative x and cubing it. Well, that's negative x times negative x times negative x. And so that will end up being just negative x cubed. Okay, so at this point, I know what f of negative x is, and I know what f of x is. And this is the even test, okay? Seeing if f of x is the same as f of negative x. And so we can say that this is not an even function because I end up with a different result. So now I move on and check to see if it's odd. So I am going to go back to my original function, f of x is equal to x cubed, and I'm just going to put a negative in front of that and say negative f of x is equal to negative times the whole thing, x cubed. And in this case, we will end up with negative x cubed. Fantastic. Okay, now I'm going to compare that to what I got before. And since these are the same, since f of negative x is equal to negative f of x, this is an odd function. Now, does a function need to be even or odd? No, there are plenty of functions that are neither even nor odd. Okay, another question that students sometimes ask is, isn't there a trick with exponents? Yes, there is a trick with exponents, but only when you're working with polynomials. And there are plenty of other functions that are even and odd that are not polynomials, so it's better to stick with the algebraic test. All right, let's move on to evaluating piecewise functions. Okay, so what exactly is a piecewise function then? Well, some might think it's a function that is very pieceful, but that's not exactly what it is. We are going to be talking about a function that is defined differently on distinct and separate pieces of its domain. So part of its domain will be defined to be one thing, while another piece of the domain will be defined to be something different. You could have part of a piecewise function be a line, while part of a piecewise function be a parabola, or part of a parabola, or a part of a circle. There's all kinds of ways you could have piecewise functions. The graphs often look choppy or disconnected. Sometimes there's even holes or jumps in the graphs as you move from piece to piece. So I've got a couple of examples here. We've worked with this graph before, and this graph has several different line segments and rays that are all connected, but they're defined differently, right? This is a horizontal line. This is a line with a slope of what, -1/2. This is a line segment with a slope of -1, and then we have another horizontal line. All of those are different definitions and different pieces of this function. Here's one that has one side of the graph being a horizontal line while the other side is part of a parabola. Anything that is defined in this way, where it's not the same definition for the entire function, is considered piecewise. So this is what a piecewise function looks like as an equation. Now notice that really it's made up of three parts. The part on the left-hand side is exactly the same as what you're used to. Here's f of x. But on the right, you have multiple things going on, and this is where it gets a little bit crazy. So on the very right-hand side, this is going to be telling you about the pieces of the domain. On one side of -3 on the x-axis, the graph is going to be defined by this line. On the other side of -3 on the x-axis, we have a different line going on. And right at the point x equals -3, we have the y value of 19, which is going to give us just an isolated point right there. So one of the things that you need to be able to do is then evaluate a piecewise function. So let's give that a whirl. Let's look at this, f of 4. Okay, so some students think that since there are 3 pieces, you're going to sub it into the 3 different pieces, but that's not exactly right. Remember that this 4 is representing x. So we need to come over here to the pieces of the domain and decide which piece of the domain does 4 fit into. Is 4 less than -3? Is 4 equal to -3? Or is 4 greater than -3? And since it's greater than -3, this is the piece that we select. Now we just sub it into the expression right here, -5 times 4 minus 4, and we get that f of 4 is -24. Okay, that's not so bad. We just need to know what we're looking at. How about this one, f of -10? Again, we're going to look at this -10 value, which is representing x, and figure out which of these 3 pieces does -10 fit into. Is -10 less than -3? Is -10 equal to -3? Or is -10 greater than -3? And since -10 is less than -3, we are going to use this piece this time. So we're going to sub in that -10 right in here for x, and then we will evaluate. 2 times -10 is -20, plus 7 is going to be -13. All right, and our last example here, f of -3. Well, which of these will -3 fit into? Is it less than -3? Is it equal to -3? Or is it greater than -3? And since it's equal to -3, we just come over here and sub it in, but there's no place to sub it in. That means I just pull this value. So f of -3 is just going to be equal to 19. All right, and that's all we're going to do with piecewise functions in this class. In our next video and last video for this skill, we will be talking about how to evaluate the difference quotient. I'll see you then.